The inside of a gas turbine engine is, understandably, very hot when the engine is in operation. Air, bled off from various positions on the compressor, is used to lower the temperature of those internal parts of the engine which may suffer from excessive heat. The pressure of the air which enters the engine is raised considerably as it passes through the compressor, and it stays reasonably high as it goes through the turbine assembly. The air bled from the compressor, which is used for cooling the internal components of the engine, is also utilized to pressurize seals, which will increase the efficiency of both the compressor and the turbine. Air bled from the engine compressor is also used to service many aircraft systems. In the modern turbofan aircraft, these may include air conditioning and pressurization, hydraulic reservoir pressurization, fuel tank pressurization, domestic water tank pressurization, thrust reverser actuation, fuel heaters, engine airframe anti-icing. For use outside the engine itself, air typically is bled from two sources. We'll use this simplified diagram to show them. The first source is an outlet on an early stage of the compressor, which supplies a continual low-pressure bleed. This continual low-pressure bleed, when system demand requires, is supplemented by a second source of air taken from the HP compressor through a control component called the high-pressure bleed valve. During high-power operation of the engine, the low-pressure bleed is usually of sufficient pressure to maintain the air conditioning and pressurization system. During low-power operation, the low-pressure bleed pressure will fall, and the high-pressure bleed valve will open to ensure both an adequate pressure and sufficient airflow. The high-pressure bleed valve is invariably scheduled to open when airframe anti-icing is selected. In this situation, the requirement is for hot air and lots of it. We know from earlier lessons that the higher the pressure at the bleed, the higher the temperature of the air. All of the bleed air supply from the engine can be shut off, if required, by the operation of an isolation valve. The isolation valve is operable from the bleed air control panel on the flight deck. The isolation valve will also be closed when the engine fire handle is operated, to isolate that engine bleed air from the rest of the aircraft. This diagram also shows fan outlet air being used in a pre-cooler. The pre-cooler controls the temperature of the bleed air going into the system to an acceptable level. The fan can also be used to supply cooling air to the engine oil system and the constant speed drive unit. The bleed air used to supply the cabin conditioning system is controlled by pack flow control valves, sometimes called pack valves. The pack valves enable the pilot to selectively control the air conditioning system and, in the event of a malfunction, particularly one involving smoke in the cabin, shut off individual conditioning packs. Air conditioning bleeds from main engines or auxiliary power units should also be closed during any ground de-icing operation to prevent toxic fumes entering the cabin. When air is bled from the compressor, it reduces the air mass flow through the engine, which has a detrimental effect on the thrust of the engine. This will be indicated on either the P7 or the engine pressure ratio gauge. Reducing the mass flow through the engine also has the effect of reducing the amount of air apportioned to cooling the combustion chamber. This will have the effect of increasing the exhaust gas temperature. Bleeding air from the compressor reduces the load on the turbine. This will have the effect of increasing engine RPM for a given fuel flow. The specific fuel consumption of a gas turbine engine will increase whenever an engine bleed is opened. Air bled from the compressor for use in the engine is used for internal cooling, for instance, cooling the turbine blades. That air can also be used for sealing bearing chambers and areas either side of the turbine discs. Air has considerable work done on it to raise its pressure as it passes through the engine. To ensure maximum engine efficiency, it's logical to extract the air from as early a stage in the compressor as possible, commensurate with it being able to perform its function. When the air has done its job, it's either dumped overboard or alternatively ejected into the main gas stream at the highest possible pressure, thus achieving a small performance recovery. The main parts of the engine that require cooling are the combustion chamber and the turbine section. We've already discussed combustion chamber cooling in a previous lesson. Here, we'll examine the cooling of the turbine section. We know from the introduction lesson that the gas turbine engine is a heat engine. High thermal efficiency is dependent upon high turbine entry temperatures. We stated earlier that there is a limit to the amount of heat which can be released into the turbine from combustion. This limit is imposed by the materials from which the turbine blades and nozzle guide vanes are manufactured. If turbine blades and nozzle guide vanes are continuously cooled, then the temperature of their operating environment can exceed the melting point of the material from which they are made. The turbine discs are also heated by conduction from the turbine blades. Thus they must be cooled if their disintegration from the effect of continued thermal stress is to be avoided. Some modern turbofan engines use cooling air to control turbine blade tip clearance. This system, which is shown here, is called active clearance control. It works by controlling the temperature of a tubular shroud which is fitted closely around the turbine casing. A feature of some engines is the selective cooling of the compressor rotor using bleed air. Air extracted from the intermediate pressure compressor to cool and seal the low-pressure turbine discs flows axially through the annular passage between the high-pressure compressor discs and the intermediate pressure compressor drive shaft. This air picks up heat from disc surfaces and the shroud. This assists in controlling the thermal growth of the compressor blades, which increases compressor efficiency. This series of diagrams shows the development of turbine blade cooling since its inception. In the manufacture of early gas turbine engines, it was considered sufficient to pass low-pressure compressor air through the turbine blade. This was called single-pass internal cooling. The use of single-pass internal cooling retained the temperature of the turbine blade below the critical level at which excessive creep would occur. The requirement for greater engine power and efficiency meant that higher gas temperatures were necessary in the turbine. Low-pressure compressor air was no longer able to provide the required amount of cooling on its own. A supplementary source of cooling was required. Research showed that by passing high-pressure compressor air through the blade as well as the low-pressure air, a reasonable increase in the gas temperature could be achieved before blade failure was experienced. This method of cooling the blades was called multi-feed. An additional increase in turbine gas temperature was attained by passing air through small holes in the leading and trailing edges of the blade. This film cooling created its own boundary layer effect. To some extent, this boundary layer protected the turbine blade from the onslaught of the hot gases coming from the combustion chamber. The process involved in cutting the small holes in the leading and trailing edges of the blade is quite intricate and involves the use of industrial laser technology. This video may give you some idea of the operation. This was the type of turbine blade which engines used for the following decade. Eventually, however, events dictated that further advances in blade technology had to be made. Engine designers and researchers reasoned that if passing air through the blade once could lower its temperature, then passing the air through more than once would lower it more. This proved to be true. Eventually, the optimum number of times the air could be passed through the blade was found to be 5, quintuple pass, and the quintuple pass multi-feed internal cooling with extensive film cooling is presently considered to be state-of-the-art in turbine blade manufacture. The nozzle guide vanes use a similar method of cooling to that which is used to cool the turbine blades. The one major difference is that only high-pressure compressor air is used. This diagram shows a nozzle guide vane which is cooled by air from the high-pressure compressor, which is supplemented by film cooling. In the vast majority of gas turbine engines, the turbine blades are fixed to turbine discs. Heat conduction from the turbine blades to the turbine disc requires that the turbine discs are cooled and prevented from suffering thermal fatigue from uncontrolled expansion and contraction. This diagram shows how the front and rear faces of each of the turbine discs is cooled by high-pressure compressor air, the actual pressure in each disc cavity being controlled by interstage seals. More on interstage seals momentarily. To prevent the leakage of oil or air into spaces where it should preferably be excluded, several different types of seal are in current use. Most of these seals work on the principle of the labyrinth, which is another name for a maze. The labyrinth seal consists of fins which rotate within an annulus of oil, or, where the exterior of the seal is static, the annulus can consist of either a soft abradable material or a honeycomb structure. In the case of the abradable material or honeycomb structure, initial running of the engine makes the fins rub against the annulus material, cutting into it to give the minimum clearance. Interstage seals are used to either prevent or control leakage of air between sections of the engine which are operating at different pressures. During operation of the interstage labyrinth seal, there is a pressure drop across each fin, which results in a restricted flow of air from one side of the seal to the other. The amount of pressure dropped across the seal depends upon the number of fins over which the air must pass. To create two adjacent zones in the engine, one at a higher pressure than the other, we use an interstage seal which has fewer fins in the access to the high pressure zone than are used in the access to the lower pressure zone. More pressure will be dropped by the air passing over the 5 fins before the low pressure zone than will be dropped over the 2 fins preceding the high pressure zone, shown in this diagram. Where seals have to be placed between 2 rotating shafts, it would be possible, if abradable material was used in the manufacture of the seals, that there would be friction between the fins and the abradable material due to flexing of the shafts. This would create high temperatures and the possibility of shaft failure. An intershaft hydronic seal, like the one shown here, can be used to provide the seal without risking the sort of problems just mentioned. The intershaft hydraulic seal is an example of the first type of labyrinth seal mentioned in this lesson. The fin, or fins, rotate close within an annulus of oil. Any deflection of the shaft will cause the fin or fins to enter the oil, and the seal will be maintained without generating any undue friction or heat. We stated earlier that, to maintain the efficiency of the engine as high as possible, the air required to perform the cooling and sealing functions was taken from as early a stage as possible in the compressor. In the particular case of the air used to seal bearing chambers, that air is taken from the intermediate stages of the compressor through air transfer ports in the compressor rotor drum, and passed through communicating passages to where it's required. The efficiency of all of these seals depends basically upon 2 factors. Firstly, the mechanical design of the seal, and secondly, the air pressure, which is essential if it's to work at all. Oil loss from a serviceable engine working at high power settings is almost negligible. It's during periods of low engine power, for instance, use of idle power during descent from high altitudes, that the greatest oil loss from a serviceable engine is suffered. If a go-around is initiated after a long stable descent with idle power set, then the engine often shows evidence of great amounts of oil being burnt and ejected with the exhaust. When cooling and sealing has been carried out, The air which has been doing the job has to be disposed of. This diagram shows that the high-pressure air used for cooling is ejected into the exhaust stream. The low-pressure air, on the other hand, is fed out through its own dedicated vent pipe. On some engines, the temperature of the air exiting through this vent pipe is monitored to give an indication of the integrity of the engine's internal construction. Any failure which causes the temperature to exceed a predetermined maximum triggers a warning via a temperature sensor. The warning consists of a red light with the caption IEOH, which stands for Internal Engine Overheat. The response to the warning is a mandatory engine shutdown. This concludes the lesson on engine air bleeds.